Question 3.1. Not too difficult a question, just unusual really. A peptide is hydrolyzed to form a solution containing a mixture of amino acids. So a peptide is a long protein chain formed together when amino acids join together in a condensation reaction, forming peptides, sometimes called amide links, carbon to oxygen and nitrogen to hydrogen link. And they can be hydrolyzed. In other words, the water can be put back, a reaction with water. You'll need some acid or some alkali to catalyze that reaction. This mixture is then analyzed by thin layer chromatography using a toxic solvent. So the solvent that's rising up the plate, the moving phase, is toxic and poisonous. The individual amino acids are identified from their RF values. The RF value is the height of the spot from the pencil line where it's been put onto the plate, divided by the distance from the pencil line up to the top of the solvent front, the top, the height that the solvent's risen to. Part of the practical procedure is given below. Parts of it are in bold text. For each of these parts, consider whether it's essential and justify your answer. So essential means it's either dangerous or the experiment would be ruined if you don't take note of it. So first of all, part 1, wearing plastic gloves to hold the TLC plate, draw a pencil line. So is it important to wear plastic gloves? The answer is I would say it's essential because you've got amino acids on your hand and that would ruin the experiment, that would contaminate the plate. The next part, a depth of no more than 1 centimetre cubed. In the developing tank, add the developing solvent to a depth of no more than 1 centimetre cubed. I think that means that if the pencil line is 1.5 centimetre cubed from the bottom of the plate, the depth needs to be below that, otherwise the solvent won't rise up the plate, it will just take the amino acids and just dissolve them into itself. So it's got to be below the pencil line for the experiment to work. I think that's essential too. If the solvent is too deep, it will dissolve the mixture from the plate. It needs to rise up the plate and carry the mixture of amino acids up with it. Place the TLC plate in the developing tank. Allow the developing solvent to rise up to the top. Remove the plate quickly. Allow the plate to dry in a fume cupboard. Is it essential to go to the top? Here, this is a bold part. No, it's not essential to go to the top. It's just better to go to the top. If it does go to the top, then your measurements are larger and you've got a less percentage error. But it's not absolutely essential for it to rise to the top of the plate. If it goes above the top of the plate, that would be essential because you wouldn't have a measurement then. But it's not absolutely essential to go right to the top. It's just good practice. Allow the plate to dry in a fume cupboard. Yes, because the solvent's toxic, so that's essential. Outline the steps needed to locate the positions of the amino acids on the TLC plate and determine the RF values. Well, you're going to have to spray it with some kind of developing agent, or you can use ultraviolet light. So we use something called ninhydrin, which means that the amino acids show up on the plate, and therefore you can determine where they are, work out where they are, and then measure their heights and measure the height of the solvent front and calculate the RF values. So you measure the distances from the initial pencil line, that's where you place the mixture, and you measure up to the spots. You measure the distance from the initial pencil line up to the top of the solvent front, that's the height that the solvent's risen to, and you divide one by the other. So you divide the distance that the spots travelled divided by the distance that the solvent's travelled, and that will give you an RF value. Explain why different amino acids have different RF values. Well, it depends on their polar bonds. So different amino acids have different polarities, different size polar bonds. In other words, their delta plus and delta minuses are different. It depends on the differences in electronegativities between the atoms bonded together. So say, for example, if you've got an oxygen bonded to a hydrogen or a nitrogen bonded to a hydrogen, then the oxygen, the hydrogen, or the nitrogen, the hydrogen are very different in electronegativity. So you get very large delta plus and delta minuses. You get very large polar bonds. And then you get hydrogen bonding as intermolecular bonding between those amino acids. So it depends on the polarities or the sizes of the delta plus or delta minuses. in the amino acids, then depending on how polar those bonds are, how large the delta plus and delta minuses are, then that determines how well they stick to the stationary phase. The correct word for stickiness or adhering is retention. Retention means that they've got large polar bonds and it sticks to the stationary phase. The stationary phase is the thin layer chromatography plate. So how well it sticks, or rather how much it retains, how much the retention is onto that plate. The larger the retention, the less it moves, and the smaller the RF value. Another way of saying it is that you could say how soluble it is in the moving phase. That's the solvent that's rising up the plate. The more soluble it is, then the further it goes up the plate. And usually that's determined on if something is polar, if the amino acid is polar, has large delta plus and delta minuses, it will dissolve in a solvent that's also polar, got large delta plus and delta minuses. It dissolves in there because you get intermolecular bonds set up.